All right, so this is for those of you that have not already had the derivative. This is the rudimentary physics derivative functionality lecture. So, okay, the definition of the derivative: it is the instantaneous rate of change of a function. That is the derivative of that function. Okay, it will often give you another function. When you take the derivative of a function, it will give you another function in the same variable that tells you the rate of change of the previous function from that function. So you have, right, so you have, okay. Okay, it also, this rate of change is described as the slope, as we talked about last time. So it describes the function, the slope of a function at any point on that graph. Okay, so here we have our little friend walking along the street again, and he's on our graph for x meters. And each one of these, let's see here. Okay, so each one of these dots we're representing a moment in time. Okay, and so it looks like, okay, he'll travel 2 meters every 1 second. Okay, so at 2 seconds he's at 4 meters, and at 3 seconds he's at 6 meters, and at 4 meters he's at 8 meters. Okay, and so we can ascertain from our graph that he's got a velocity of 2 meters per second. Positive 2 meters per second. Yeah? Okay, that's pretty straightforward there. Now, if we were to plot his position against time, okay, we get these points, and you'll see that I get these little drawing things in there to make sure that I'm getting our points in there right. And we'll find that this line, okay, has a slope of 2 meters per second. So we can take any two of these points. Say we're right here at, at 2 seconds and 4 meters, and up here we take another point at 4 seconds and 8 meters. We know that slope is delta x over delta t, which is our change in position over change in time. Okay, but we can rearrange this to give us our slope, which is 2 meters per second, times our time is going to give us this function of his position in regards to time. Okay, and that we've created this function of x of t, which is his position, which in this case is just his slope with the slope times time. That's what his position is going to be. Just, okay, very straightforward. That is the linear constant velocity situation. Let's take the same graph. Now, what we're going to make here is called a kinematic stack, and we're going to have a number of these through the year. And what we're going to do is we're going to relate position to velocity to acceleration on 3 separate graphs, but they're going to be aligned with our bottom, with our independent axis. Okay, so the t-axis in this case is going to be the time. So in this case, we're going to make our velocity time graph based on our position time graph. Okay, and so we draw these vertical lines here. You guys can you see the blue? We should turn off the lights here, so I'm going to pause. So when we create our velocity time graph, we're going to be tracking our time as we go down, and at each second, though, with our velocity, we've got a 2 second. Each time we have a velocity of 2 meters per second. Okay, which creates this line. So our velocity, okay, our velocity time graph is going to be this horizontal line, okay, at 2 meters per second, which is derived from our vertical or slanted line for our position versus time. Now this should make sense that our slope, if our slope is our velocity isn't changing, so it will always be 2 meters per second. This is the other definition of derivative. This is the derivative case. This is the basic, the trivial case for, or one of the trivial cases for our velocity. Okay, so again, our velocity time is 2 meters per second. Okay, but we're going to do another one. And this time, our position versus time looks like this, where we have a changing position over the time. Okay, and it's not just increasing at the same rate. Okay, so we'll make a velocity time graph. Below it, we're going to make this kinematic stack. And over the first time period, as we're traveling along here, okay, we have a slope. Well, according to the graph, it's 7/5, but we're not really going to worry about. This is a qualitative version rather than a quantitative version. But we do have, it's positive. The slope is positive. Okay, and it goes until this time right here. And so we can create. We do its velocity, which is a constant velocity, and it's positive, and it's above, okay, it's greater than 0, so it's going to be horizontal. All right. Now, I don't know if you've seen in there, but I've drawn 3 blue lines that correspond with key points in, I'll draw them again. We've got one here. They're not so light anymore. These are key points along our position time graph. Okay, it's when our position changes or when our state of motion changes. Now, what happens for our next period of time? If we're horizontal right here, what's happening to our position? Okay. Our position is constant, right? It's level. It's not changing. We have no change in position. So if our change in position is 0, and after so many seconds we haven't moved at all, then our velocity is going to be 0 as well. And so we'll have a velocity that is right on the time axis because we have a 0 for our time axis. And then we keep going from there, and after that time period, we change our state of motion again. And all of a sudden, we are changing our direction, but we're changing our direction. We're actually headed back to 0. Okay, and we're doing it a little steeper. So our velocity, the magnitude of the velocity, is going to wind up being further away from the axis than this one. Okay, and it's going to be negative. And so we're going to get down here further away than this is up here. Okay, and this is our kinematic stack. Okay, for position and velocity. We good? Got it in there? But, okay. This is just for, again, for simplistic cases and just when we have constant velocities. What happens if our position versus time function is actually realistic, how things actually move? Okay, there are no sharp turns. Okay, if we were to actually experience a constant velocity and instantaneously stop, okay, it would hurt a lot.
Like hitting a wall?
Yes, like hitting a wall. Okay, but even so, hitting a wall, you have a minuscule amount of deceleration, and we'll get into that a few chapters later on when we start talking about impulse and momentum change. But the amount of time that it takes to hit the wall, the shorter it is, the more it hurts. Okay, the longer time it takes for you to come to a stop, the less it's going to hurt, which is why boxers wear gloves. It's so their hands can inflict more damage upon the head that they're hitting. Okay, they protect their hands, but they hurt the head. So, but we'll get more into that. That's a couple units from now. Okay, so in other words, what if the graph is curved? Okay, so we create our kinematic stack again. Okay, but we'll have, in fact, let me do that even better. There we go. Okay, so we draw our curve. Okay, just a basic curved position. Now we can talk about it where he's already a certain distance from the origin, then he's getting closer, he's walking back towards it, and then he kind of turns around and walks further away, and then he turns around and walks back closer to it. All right, now for a curved, there are other points of interest that we need to track down to our lower kinematic stack. Okay, these look familiar to you, and in particular, they are points where our velocity is going to be 0, okay, or our velocity changes from increasing to decreasing. Okay, there are two different moments. So, the first one I've drawn in here for you, this is when our velocity is equal to 0. This is when our position, this is a turnaround point. This is where we stop walking back towards the origin and we start walking away from the origin. Yeah? Okay, there's another one over here. This is another 0 point. This is where we're walking away from the origin and we turn around and we walk back towards it. Okay, and the curve implies a gradual change there. Okay, but there's another point, and it's right about here, where we're walking away, and then our curvature changes to where we start actually walking towards again. I'm sorry. It's what I'm trying to say. We're walking away. We're walking away faster, but then we start to slow down again. It's like at this point right here where we change our mind, and we curve back. This is called, okay, we change from a concave up to a concave down. Okay, and this point is called a point of inflection. It's when our concavity changes. And it's that point right there. And it means something different on our velocity graph. Okay. So what does this look like? Okay, so let's examine the slope of x of t. Okay, so at any given time, as we're heading towards our first point of interest here, okay, well we know that here, this is a turnaround point, but what happens when we turn around? That's where velocity is going to equal 0. Okay, we also know on the other side that as we are finishing our walk, we came from a point where our velocity equals 0. Because anytime we're turning around, we're changing our direction. Our velocity is going to change signs. But this one's an interesting one. This is where our concavity changes, and this is where our velocity goes from increasing to decreasing. Okay, we can also have one in the other direction. We can have a velocity going from decreasing to increasing, and it would be a similar, okay, the curve would just be down like that instead. All right, so at this point of inflection right here indicates that our velocity is changing directions. Okay, that we're going from a positive velocity. Sorry, we're increasing to decreasing right here. Okay, so our slope is going to be our change in x over change in time. Now, so how do we mathematically then determine what the velocity is when we know what the function of x of t is? And to do that, we come up with our derivative. So let's draw our function here, our sample function here. Okay, and it's x of t. X is our dependent, t is our independent. Okay, and we're going to try and find the slope of x of t at that point, right there. Well, here's what we're going to do. We are going to find the average velocity around that point, near that point, and we're going to create the time over which we're taking the average, and we're going to shrink it down to 0. So we need to come up with another line here. Okay, and so what we're going to do is we're going to add a certain change in our time. So here is our time initial, and here we are adding a certain addition of time, and we'll call it delta t. Yeah? So this point down here, okay, that t coordinate is going to be t plus delta t. Whatever this t was, plus the delta t is going to give us t plus delta t. All right. Now, that also corresponds with a change in x. So if we have an x of t over here, this point's going to be x of t. Okay. Then when we add delta t, we're also going to have a corresponding x of t plus delta t. Are you with me so far? All right. These 2 points are going to, if we wanted to create a line between these 2 points, that would be making the average velocity from time t to time t plus delta t. Right there. So the slope of that line, okay, would be the average velocity. Well, what is the slope of that line? Okay, we know that it's delta x over delta t. And so to do that, we're going to take the difference of the y's and divide it by the difference of the x's, right? Well, the difference of the y's is going to be this x, t plus delta t over x plus t, minus x plus t. And the difference of the y's, the difference of the time is going to be, sorry, I know I'm saying this wrong. Our bottom is going to be the difference of our times. So it's going to be t plus delta t minus t, which winds up just being delta t. Yeah? So this is going to be the slope of, this is the average velocity of between these 2 points. This is the slope of this line. However, we don't want that. We want to make our time, okay, we want to find the slope at x of t. And to do that, we have to shrink delta t to a minimum, to a 0. And we do it like this. We use the limit operator. That velocity, that our v of t, is going to be the limit as our delta t approaches 0 of our slope. The limit as delta t approaches 0 of our slope function. This, by the way, is the definition of the derivative. Okay, is manipulating this and solving this particular equation for any particular function. Okay, now, if we are to zoom in on that orange circle right there, we would have a really small delta t and a really small delta x, right? They'd be very, very small. Okay, both of them are tiny, infinitesimals. And we have a symbol for infinitesimals. Okay. Oh, but they're not 0. They're not 0, because if they were 0, then this wouldn't work. Okay, so our delta x over delta t could be a whole bunch of zeros of the 2 at the end divided by the same number of zeros of the 1 at the end. Yeah? Okay, whatever those are, it's still going to be 2 meters per second. Right? Even though the 2 terms are really, really small, if you divide them, you get 2. Okay, so we still have, our equations still have value here. Okay, so here's our example. let's go back to our first function that we had, our velocity way on the first page. If x of t is now 2 meters per second times t. That's more than I wanted to show you yet. Okay, so we can do all this. And that's how you plug it in. So we're going to have 2 meters times t plus delta t minus 2 meters times t all over delta t. And we keep manipulating. And we solve this. To find that, yeah? Do you guys see anything that cancels? Okay. Well, eventually, yes. Okay. But you've got a 2t here and a negative 2t over here, right? Those two are going to eliminate each other. Okay. And then we have our delta t. Once those are eliminated, then we can divide out the delta t's on top and on the bottom, leaving us with a v of t equaling 2 meters per second. But again, this is the trivial case. This reduces to a constant. But we knew that because we had the horizontal line. All right, easy, right? Piece of cake. Just wait. It gets better. What if x of t is complicated? Just a little complication. Like, what if x of t is 2t squared plus 1? We still got to plug it in there, which means we've got to throw it into our t plus delta t gets thrown in there. So we get 2 times t plus delta t squared. Yes, we get to do a binomial expansion. Yippee. Plus 1 minus 2t squared plus 1. I can't believe I actually did this for you guys. All right. So, when you multiply it all out, you get that. Two times quantity t plus delta t squared, which is t squared plus 2t delta t plus delta t squared, plus 1, minus quantity 2t squared plus 1. All right, and now we need to start simplifying again. Oh, and it's the limit of that, by the way. I forgot to put the limit in there. The limit still needs to be there. So, once again, it's the limit of expanding out 2t squared plus 4t delta t plus 2t squared plus 1 minus 2t squared minus 1, because we distributed the negative in there. Make sure you do that because that's the source of many an error when you're doing a derivative from scratch. The 2t's are going to cancel. All of that stuff cancels, leaving you with four t plus 2 delta t. Yeah? You guys follow the algebra there? We're good? All right. But if it's the limit as delta t approaches 0, then what happens to this term right here? Goes away, gets lopped off. And 4t equals dx dt. And dx dt is our mathematical operator for the derivative of the function x of t, is dx dt. Okay, in fact, the operator itself, yeah, are we good here? Can I flip pages? You guys are caught up? Yeah? Slow down? We're good? All right. Limits suck. We hate doing them. They are a pain in the butt. Okay? Particularly limits as far as the definition of the derivative. They suck. So, wouldn't it be nice if mathematicians came up with a way of solving that took much faster than doing that whole limit thing? I say thee yes. There is. And it is called the power rule. Okay? And let all of us rejoice. Imagine, if you will, doing the limit for this particular function. 5t to the fifth plus 2t cubed minus 9t squared minus 4 plus 9t squared minus 4t plus 8. And having to do all of that long-term x delta t. Imagine doing the t to the fifth expansion of t plus delta t. Yes, if you have the Pascal's triangle, 5, 10, 10, 5, 1, or whatever it is, memorized, that makes it a little bit easier, but it's still a colossal pain in the rear. But if I could tell you that the actual derivative of this thing is, 20t to the fourth plus 6t squared minus 18t minus 4, don't you want to know how we do that? Yeah. I say the yay again. So, v of t actually does equal this, and here's how we figure it out. Okay, this is the first example of the power rule that we explained the power rule. If x equals some constant a times variable t to the n power, dx dt, which is the derivative of the function x at t, is going to equal that power, this n right here, gets multiplied out in front. You keep that constant, and then you subtract 1 from the exponent.
Should it be 6t squared?
Shut up. Happy now? Thank you, Harris. This is something that those of us that know calculus fall into frequently. We forget how to do arithmetic. Okay, it's true. We forget how to do arithmetic. Okay, so this is our first power rule. So we take this n right here, we multiply it times a. We get nat to the n minus 1. We subtract 1 from this power. Okay, so our example is going to be 4t to the 7th. The dx dt will then be dx dt will then be the 7 times the 4, 28, times t to the 6th. That's it. That's the derivative. That's it. Piece of cake. Okay. Here's another cool one. X equals e to the at. This also works with exponential functions. This would really suck to have to do the definition of the derivative. Luckily, we don't have to. In fact, e is very nice. The derivative of e to the t is e to the t. It is actually the derivative of its own function. So, if we have e to the at, then we would multiply, and we would drop this a down in front, and the rest of it would stay the same. And so d dx would be a e to the at. See that? Okay. Okay, and there's one more. Okay. Sine a of t. Okay, the derivative of this will be a, bring that a out in front, cosine a of t. Okay, and we're going to see sines and cosines quite a bit. Okay, so the derivative of sine a of t, sine at, you can throw the a out in front, change the function to cosine to become t. If we go backwards with it, cosine, okay, it kind of gets lost in all of the, but right here, the derivative of cosine is negative sine. And so cosine of at would be a negative a sine a of t. But you could probably see how it cycles back through. Then if derivative of sine then is cosine, derivative of cosine is negative sine, you can keep throwing, and it would be a positive and negative cycle for sine and cosine. And I believe that is the end of our derivatives lecture. So